Good morning. Ooh, why do I have that in? Good morning. Good morning. 1 second. I just realized. Good morning. Okay. Good morning. Who do we got? Good morning. Can you hear me? Good morning. There's Lunar. Good morning. Good morning, Jalila. I'm looking at the videos. I'm looking at the visuals. Good morning. Oh, Jalila for the double. Good morning, Melanie. Good morning, Lunar for the double. Two moons, like Mars has two moons, Phobos and Deimos. But she knows that. All right. Good morning, Nadine. Good morning, Luke. Good morning, Alicia. Good morning, Josh. All right. All right. Awesome. And anybody else? I'm saying hello to anybody saying, okay. People are still coming in. Michelle. Okay. Oh, Miss Jaden. Sorry. Okay. Um, and Jalila for the double. Or did I say that? I said that. Okay. Let's get rolling. Now I'm going to ask you a question. This is interesting that we have like the half. I kind of like this half live, half. Oh, and there's Jaden. Good morning. Good morning. Awesome. Okay, and I will. I know the view is distracting. It's just sort of fun to start this way, but I'm going to ask you to remind me. ex- Right. So we're just going to get rolling, continuing to go over homework 1A. I these are. Can you remind me exactly how, because you're live, you're in person on Tuesdays, on Mondays, and then we're electronic on Wednesday. So I'm slightly confused exactly where we left off. And good morning, Dechen. Thank you. Good morning. Could someone remind me like the last thing you wrote down in your notes on Monday? Because I'm getting confused. Like put it this well, here, I'll show you. Like um did we I believe, well, here's what I believe. I believe we're right in the middle of question four. Like, I think we did not finish it, but we started going. Oh, we finished. Oh, we did. Thank you, Nadine. We finished going over question four. Fantastic. Even better. Okay, great. So then when I put up the PDF today after this class of the notes from today, it includes some little review of Monday, which is good. Like in other words, what Nadine is telling me. So like we talked about conservative forces and how a conservative force does a net work of zero around a round trip and therefore can be associated with a potential energy function, right? And so we got the potential energy here. Like for example, I didn't write it exactly this way on the board, but like we integrated Hooke's law and got the potential energy for a spring. Just confirm. We did great. Thank you, Jalila. Thank you, Nadine. That is points for both of you. Fantastic. Okay, so we did all this. So we got to here. Great. So I'm just gonna and one little thing I may not have said. I'm gonna switch the view on the screen. This is distracting. Hold on. Okay. One little sidebar for notes. The word oscillate, like what we're talking about here is oscillation. The This mass is oscillating back and forth on a spring. Um, from here on, so we very much care about oscillation in this class. This is a study of a certain kind of oscillation. Oscillation in general, from here on in, means any kind of motion that is cyclical or periodic. Those are two words essentially for the same thing. Motion that goes over and over and over again in some kind of cycle, and for which the cycle has some sort of periodicity, i.e., something about the cycle is predictable or patterned over time. That's what we mean by oscillation in general. Certainly, a mass going back and forth on a spring is um, is a kind of oscillation. Now, it turns out it's a very specific kind of oscillation. That's where we're eventually trying to get to in question 9, which is really the goal of today. I'm gonna, if we did question 4, that's fantastic. We're gonna get to question 5. Let me just summarize just for your notes. So in other words, where we got to on the board, I'm just gonna write this quickly so it's clear. again, this is what I'm going to upload. So if any of your notes for Monday, or if you weren't here Monday, if any of your notes were unclear or incomplete Monday, they might be slightly, or also if it got confusing because I had to say so many background things about conservative force, etc. If you want to see it like as a homework solution, it'll be there when it's uploaded today. So therefore, let me just quickly finish exactly. So here we're saying this is for those people who just joined, I'm just completing what we did uh, for question 4 on the homework. Whoop. So stop me if any of this, I'm just writing it down. Stop me if any of it is unfamiliar or unclear, but we said that. We said that. So we said that. Oh, sorry. And tell me if you need me to go back. But again, this is just so that we're all on the same page. So we said for question 4 at x equals 0, v equals approximately, sorry, approximately 3.87 meters. I just made the mistake that I criticize other people for making. Okay. That is the final answer for question 4. That was on the board. You're telling me we did that. And now, again, stop me, but if I'm understanding correctly, we're now on to question 5. The good, we're actually, could someone just, so we're like totally on to, yes. All right, great. I love this class. Thank you, Jalila. Thank you. I saw other people. I think it was Lunar. Yes, thank you. Okay. All right. So we're totally on question 5 now. The good news is, the good news is that this should be really fast now that we did all this heavy lifting for question 4. Question 5, I'm going to cut straight to the chase. In question 5, we did all that work so that we can get, all right, straight to step 3, really. Like question 5, okay, I really want to model this correctly for you guys. Like, again, step 1, we would say diagram above. Step 2 is when V equals 3 meters per second, what is X, right? That's the question of step 2. So what I want, that is the same question as question 4, right? I mean, it is a speed spot correspondence. In question 4, I named the spot, you had to find the speed. Now I'm naming the speed, you have to find the spot. But whenever you have that situation of a speed to spot correspondence, it's energy conservation. That was really why I talked for so long on Monday, is to get that point across, is that if you're trying to know the speed from place to place, and yet the force changes from place to place, that calls for work and energy. So it's the same deal, right? But the other reason I talked for so long on Monday, well, that's because that's what I do. But really, what I was trying to emphasize on Monday is that the GDP here, the step 3, the principle here is energy conservation. And the principle of energy conservation is not kinetic energy equals potential energy. Again, many websites, and therefore many websites from which many like AIs pull from, whatever I'm saying, there's a like misunderstand this. Like honestly misunderstand, like they think or they say things that then lead other people to think, oh, kinetic energy equals potential energy. That is not what we're saying. in question 4, nor in question 5. We're saying the sum of kinetic plus potential at any one spot equals the sum of potential plus kinetic at any other spot. So the thing we did all this work and integrating and all that, like yesterday, Monday, the statement that applies to both question 4 and 5 is, I mean, if you want to get straight to the mathematics, is 1/2 mv squared plus 1/2 kx squared at a spot that we know, for example, equilibrium, must equal the kinetic plus the potential at a spot that we're solving for, a spot that we don't know. Great. That's the statement. And I'm also trying to model for you. I want to emphasize, like, and you can even say this, like, if this were your homework or if this were an exam or whatever, from question 4 above, so the pattern here, and again, this goes back to what I mean by self-sufficient document. Like in question 4, it may not have been the first time in our lives, but it was the first time in this document where something about energy is coming up. So say this was an exam, or say this was a research paper, a paper for a journal or whatever. Blah, blah, blah. Like it's the first time energy as a concept is coming up, and it's like a big concept, and it has a lot of nuances. Da 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 da. So in question 4 above, we do a heavy lift. Like I do a heavy lift with you guys. I do it my way. Try to get the concept as clear as I can to you in your way. Then you in the homework or on the exam, you do a heavy lift in question 4, like really explain what energy means or how you get potential energy for a spring. Like go a little overboard because assume your reader is not me, or assume it's a tutor or who, right? It's like a smart audience, but not an audience that has been hanging out with you for the last 3 weeks on this like topic. So you build the kind of energy concept all up, or the potential energy concept all up in the question 4, but now it's established in the document. It's now established. So now we can use it. And that's what I want, that habit of like a document is an experience, really. Again, whether it's a journal article or a crime lab report or or an exam, like the document is an experience that stands on its own. So you go overboard whenever you're introducing a concept, and then you assume the reader is with you and can deal with the concept. So okay, so there's the concept right there. The 1/2 mv squared plus 1/2 kx squared over here equals 1/2 mv squared plus 1/2 kx squared over there. Like for any kind of like spring situation. So we've established that above. So now we can use it, like get straight to it, right? But now I say, okay, just like we did. Oh, sorry. So now I'm sorry. This is it? Oh, that's step 3. Okay. So now step 4. Okay, so that's step 3. A lot shorter than before. That's why I really focus on step 3s. And again, in terms of the grading, well, no, I'll keep going. I think you get the point. So step 4 now, I would say like here, at x equals x naught, v equals 0, right? So i.e., I don't know how you do this on your document, but I'm saying, okay, so I can cross out that term, but my key point, and I will go on, just like I crossed out that term in question 4, but I can't cross out the 1/2 kx squared on the other side. That's the key difference here, right? That's why I'm saying, so in other words, I have here in step 4, and if you want me to go back, you can tell me, I'll look at the chat in a second. So I'm saying 1/2 kx like naught squared equals 1/2 mv squared plus 1/2 kx squared, for which like that almost looks like you could. So I'm saying the potential energy at the initial position x naught equals the kinetic plus the potential at the spot we're looking for. The spot we're looking for is called x. It's not 0, it's x. It's what we're looking for. So it doesn't go away, and it's not the same x as on the left side. at that spot, there is kinetic energy because we've been told we're looking for the spot where the speed is three, like not zero, three, right? So the spot we're looking for has both kinetic and potential. I'm oversaying this, but I'm really trying to get across that you don't ever want to. There's a tendency to believe or just to write down without understanding that, like, oh, there's kinetic over here and there's potential over there. No, most arbitrary spots, there's both. And it's just the entire sum that is remaining constant. So it's like a washing back and forth between some potential, how much potential do you have and how much kinetic do you have? That's what's fluctuating throughout the motion. Um, Last thing now, this 1f(kx) squared that the left side that equals the right side. So, okay, in English, what we're really saying there is we're saying the total potential that you have at the beginning is the total energy that you have anywhere else. In other words, the total amount of energy that you have throughout this whole thing is 1f(kx) not squared. Like, because at the beginning there was no kinetic. So a lot of people in their homeworks wrote down one half, something like what I wrote down here, but they wrote 1/2 Ka squared equals da 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 da. Now I know, now they're right. In other words, they used A instead of X naught. Many people. Now, this is not a criticism. This, again, just like a explanation for why you might not have gotten all the points, how you can get the points back, or like what to do in the future. But you might have lost points in more than one category if you did this. So if you wrote 1/2 Ka squared, or even started with some statement like the total amount of energy this mass will have throughout is 1/2 Ka squared. Well, yeah, you're ultimately landing at the same logic that I am. You're saying, well, the total amount is all of it, potential plus kinetic. And if I choose a point where there's no kinetic, then that total amount of potential there is what it has throughout the whole thing. Fine, fine, fine. But how can I say this as delicately as I can? You're using the letter A to mean what I'm using as X naught. And ultimately, I will too. You're using the letter A because A stands for amplitude. And amplitude is a way of talking about the maximum displacement from equilibrium. But if you never use the letter A before question 4, question 5, if you didn't put the letter A in your initial diagram to show me what you mean by A, then A is just coming out of nowhere. And the statements about A are just coming out of nowhere. Like, I'm not saying they're not true. I know what they mean, but they're not related to the work you're doing here with this spring. If we've defined things in terms of X naught, in other words, what I'm saying is this is where the labels in the diagram become so important because A, it just gets introduced like spontaneous combustion if it hasn't been attached to as a label to your initial diagram. And to be really honest, if suddenly things are saying things about A in question 5 or question 4, that's a strong signal that just a bunch of work came from AI. I mean, to be really honest, like, and it's not that the work is wrong, but you can't just lift it like that. Like, I'll move on. But I think this is what, and that's why, if there was an A in your homework, and I'm not shaming you, you're just going to redo it and give me, and I'm not saying you committed an ethical violation, but you're just going to redo it and get the rest of the points. But I'm telling you that if 1/Ka squared suddenly appears in question 4 or question 5, you may be losing points there and losing points under self-sufficient document because that document is not self-sufficient. Like, you see what I'm saying? You want to you I think you see what I'm saying. S- um okay, so I'll go on. So we have this. It doesn't mean A is wrong. It just means, like, tell me what A is before you use it. Okay, so we have this. So we cross out the 1/2s. Um Now we're solving for X, right? So again, habit pro tip, I would rearrange this. Oops, sorry. I would rearrange. And again, you may not, oh, sorry, I would just do that. Um, so then I would say, and you may not, you may plug in the numbers first, and I wouldn't take off points, but I really think this is a good thing to practice now while you can, because things get more, they start looking more like this. I know someone's here. Okay. So you get this because we're solving for X, right? I'm looking at the chat. Okay, because we're solving for X. And so now I'll plug in the numbers. And technical point, I think one of you raised this on Monday. Well, it might have been the other. I'm saying plus or minus because mathematically, like if I'm saying that the number squared has to equal 9, for example, then the number could be 3 or it could be -3. And the reality is that's really true here in the physics because the question is asking find the spot or find the position where the speed of the mass is 3 meters per second, right? I believe that's what the question's asking, where the speed is 3. So that means the velocity could be +3 or -3. We could be finding a spot where the thing is going this way or going the other way. In other words, we could be finding a spot on the right-hand side of equilibrium or the left. Like the question does not restrict it. So really, there really are two possible answers to this. And once you do the math, sorry, well here, so I'll just cut to the chase. So you plug in the numbers. Sorry. And that V that you're plugging in is 3 because that's what the problem specified. That's like the point of this question, right? And everything else was known from, that's what the question specified. Everything else was known from the facts of the problem. So step 5 for this is that when at V equals 3 meters per second, I could even say plus or minus if I want, then X equals a plus or minus approximately 0.09. I did it again. See, no wonder you guys. Okay. Right. This is my answer. Basically, I'm saying my answer is 0.095 meters. I'm saying, strictly speaking, it's plus or minus. To be super honest, I think if you left off the minus, if you just said plus, you probably didn't lose points for that. I'm just telling you that that's really true. There's something else about answers. In terms of significant, also, I just hope, I'm saying approximately. That doesn't mean I'm guessing. And it doesn't mean it could, it doesn't mean, it means I took the square root of, I took the square root of a not perfect square. So I'm chopping off digits. As far as significant digits, just the rule of thumb is you should try to, this is not chemistry. We're not in a lab. So that's not the biggest focus of this, the significant digits, but a good habit of physics thinking is leave your answer to the same number of significant digits as the maximum number of significant digits that were ever presented in the problem. That is the opposite of what we do in labs. If you're really trying to be conservative in an experiment, you give the fewest significant digits that you can, because otherwise you're lying. But in a problem, if you're just trying to stay on the scale of the problem, in other words, the K was given as 200 newtons per meter. Yeah, so that sort of indicates we can go up to 3. That was the most significant digits that was given in the fact pattern. So it sort of indicates that we want to go as far as 3 digits, but no farther, and maybe not. So that's a rule of thumb. So I would say the speed was the velocity in question 4 was 3.87 meters per second, and the position here is approximately 0.095. Okay, that's not a big, but what it isn't is like 0.1 something, which a lot of people get if they don't do this. In other words, this question is the same as question 3, as question 4, but it is harder. Many people get question 4 correct, and they get this incorrect because they're getting question 4 correct for kind of incorrect reasons. This is all a big lesson in taking step 3 very seriously. I'm going to go on, but okay, so that's the answer. And I'm looking at the time. Okay, that's the answer for question 5. When I say I'm gonna go on, I'm not gonna say anything more than that. I'm putting down the cannoli. But if I'm gonna go on, and I'm gonna go kind of fast through questions 6, 7, and 8. In fact, I'm not even gonna do step method. I'm just gonna talk about them so we can get to question 9, which is really the issue here. So let me pause for a second. Are there any questions, honestly, any questions or observations or concerns regarding question 5? Oh, thank you, Josh. That is totally. Do you see how helpful that is? That is points. He should submit in the portal for the points. because I'm going to say now I can go on, even though, of course, my tendency is to want to go on for 15 minutes about how I can go on. No, thank you, Josh. Okay, fine. I'm going on. Um, okay, so question six. Question six, yeah. Okay, I'm going to skip some steps here in question six, seven, eight, and just get punchlines because I just and you can be obviously questions six, seven, and eight are um more conceptual. You still do the steps, but you can always say something like you can say when in doubt, you could say something like whatever, step one diagram, see above. You can always do that, right? But then in step two, you could do step three, or if you see, if you think something's not applicable, a step is not applicable, you could say step four, not applicable here because whatever, but just acknowledge it. Okay, but I'm not doing that now because I want to get to the points. So we're talking about question six. Question six. I, Now stop me from wrong. I believe question six is like how far does it go on the other side, right? How, right? Uh, if anybody can confirm, because I get question six and seven confused, but I believe question six is like how.
Yes.
Yeah, oh, thank you. Ooh, and that was voice. You could submit for points for voice. Thank you. Okay, and thank you, Nadine. Okay, so I'm going to cut straight to the chase. If you think, if you think this one, it was not a trick question. If you ever think, I think this is kind of straightforward. Oh, but this is physics class and everything else was really confusing. So he must be a trick. No, don't. If you think you have an answer in your mind, I'm not, don't, I'm not trying to trick anybody. If you think that the answer should be something like that, you're correct. And if you're just thinking that because you're thinking intuitively, I just feel like I mean, it should just do the same thing back and forth, the same thing. You're correct. But now what I want to tell you is that's because if you're thinking it should be symmetric, you're correct. And what you're really realizing or thinking is you're correct that this situation should be symmetric, like in time and in space, but it should be symmetric. Like anything that happens, anything you believe is happening on the right side should be happening on the left side. Anything, as it turns out. Um, but what I want to tell you quickly is, in terms of your homework or whatever, how you can show that. Like the truth of the matter is, this question again, if you do the same method as you did in question four and five, skip all the integration of everything, but get straight to like KE plus PE over here equals KE plus PE over there. If you do out the math and solve for when X, excuse me, solve for X when V equals zero, that's what you're doing, right? You're solving for the other place of X when V equals zero, you'll get the same thing we just did. You'll get two roots, only instead of them being like negative and positive 0.095, they'll be negative and positive 0.15. You'll see it's two roots. One of the roots we already knew was positive 0.15, but it'll show you that the other root has to be negative 0.15. It's because energy is conserved that everything is symmetric. So the math will show that again. I'm just saying. So I'm saying that. Um, and then so the same thing with the next question, really. And stop me. I'm just trying to go get to it. But if you don't, I'm just assuming you sort of understand this. But if you don't, please do stop me. So question seven was like, how many cycles? How many? I can always tell I'm being too crazy. Literally, the dog is barking. So that means I'm yelling too much about physics that does not warrant yelling. Okay. How many cycles? And if you think the answer here is infinity. You're right. Um, it is. Now, and quick pause on this too. You might think, okay, that's such BS. Like, this is why I hate physics. Like, infinity, really? Like, this thing is really going to go on forever? I mean, we just had a freaking lab about this a week ago, and the thing did not go on forever. So, like, what, fictional world are you living in, Yaverbaum? Well, fair enough in a way. And don't get me started. I could rabbit hole on this forever, but I'll put it this simply. Right. We are talking about an optimum spring. The ones in the lab are kind of cheap and kind of small. Bigger, more expensive springs. Really, it's not bad about expensive, but the bigger the spring, the bigger, the tighter, the more uniform the spring, the more close to this truth it will reveal. And at a certain point, the spring can be big enough and tight enough to achieve these results beyond the threshold of measurement. Okay, this is where I could really go crazy on this, but it seems often when we're doing physics, it seems like we're doing all this math, and the math is like ideal world, but the real world of science would say like, no, that's just like all idealization on your part. But actually, it's the other way around. Actually, from a scientific point of view, is where all these seeming ideal predictions really are too, because in science, something is only true if we can measure it. We can only talk about numbers that are that are measurable. So once something succeeds past the threshold of measurement, then there's you can't talk about its failure anymore. And I mean, again, this is a whole discussion, but just think about this. In other words, the simpler way to put it is we say, oh, assume friction is negligible, right? We say, assume this thing conserves energy, assume that the friction is negligible. And everybody, including me, of course, the first 50 times we hear this, we're like, really? Assume the friction, assume I can neglect the friction? Like, am I on the moon? I mean, seriously? But all that means is assume that the friction is having such a low effect, like it's slowing down the system by such a small amount that you can't even tell in the measurements that the system is not losing a measurable amount of light, and that is totally constructible in the lab. Not our labs, we're City University, but the government, when the government funds MIT, they can do, you know what I'm saying? So it's not actually a lie. It's in the limit. It's an asymptote kind of thing. Okay, and the last thing I'm going to say too. I mean, I'm just a little defensive because from here on in, we're going to talk about, ideal oscillators. Like this problem is just setting us up for doing all the math of really good oscillation like this. And I just want you to understand that it does apply to the real world. Oh, also, okay, wait, sorry. Really, why we're talking about all these oscillations. We're picturing a mass on a spring and what it would do, like in our head. And yeah, it doesn't do it that well in our labs. It does it just well enough to give you a mental picture, but then you have to extrapolate that mental picture to a better version. But the real reason we're talking about this, where does this really happen? Like infinite cycles or like perfect symmetry? Where does this really happen? In the oscillatory nature of atoms, like in the real world, underneath the world that we build, atoms are oscillating all the time. Water molecules are oscillating all the time and making water waves. And they do behave like this because there isn't friction within an atom. So honestly, that's real. And we're really building all this so that these equations and these concepts of oscillation for PChem, where it's totally you're talking about atomic microscopic systems, where this totally applies. Just so okay, so it's not just BS. Okay, so the answer is infinity for that. Okay, so now question 8. Stop me. I'm just looking in the chat. Okay. Oh, we still have 40 minutes. Okay. I'm going to slow down a little once we get to question 9, but I'm just trying to get to question 9. So then, question 8 was, is this is a little bit more interesting. Question 8 asks, like, Okay, so question 8 is asking if you picture, so we're now viewing this as an oscillatory cyclical motion. Oh, yeah, like, right? I mean, we're saying that we're picturing that you let this mass go from x equals x naught. So it'll start moving in toward the equilibrium. And our numbers indicate it'll be moving faster and faster as it goes to equilibrium. But it'll be really moving very fast when it gets to equilibrium, 3.87 meters per second, right? So it, sorry, at the beginning, it has all this potential energy, no kinetic. Then it starts moving into the equilibrium where it'll have all this kinetic energy, no potential. So it'll have maximum kinetic energy at equilibrium. You might want to write this down. Like the pattern is maximum potential to maximum kinetic. Zero potential, but maximum kinetic means it's moving as fast as it's ever going to move, right? So it keeps going, right? I mean, I know in one part of our brain, we all know this, but again, it doesn't stop at equilibrium. It keeps going into compression if it's an ideal spring. And again, that just means a really long spring that's really uniformly tight. So it keeps going, but now slowing down, slowing down, slowing down until it gets to zero speed, i.e. minimum kinetic, maximum potential on the other side. But notice too in the back of your mind, I guess we're about to do this, but notice too in the back of your mind, while the potential's going down and the kinetic's going up, the same thing is happening to the acceleration, the force, right? The net force, the acceleration is minimum at equilibrium, zero, but it's maximum at the end points, at the turning points, right? So okay, so it's going to cycle back and forth, going like faster, 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 slower, 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 faster, 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 slower, 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 and do that forever, right? That's what we're picturing now from now on as oscillation. And we're picturing these cycles, a full cycle from now on. A full cycle is a closed path, a round trip. If I say cycle, I mean all the way there to negative 0.15, like on the other side, and all the way back, right? That's what I mean by a cycle. So we're now going to examine the first fourth of that cycle, just what's going on to the magnitude of the following measurements or the following quantities just in the first quarter of a cycle. And we're just looking at magnitude, right? So we're asking what's happening to the magnitudes of velocity and acceleration. And then this new concept that we never talked about in Physics 203, jerk. In other words, now that's a new concept, but I'm assuming from math that you can picture the concept, because really what we're asking here is derivatives, right? We're asking what's happening to the first derivative of position with respect to time, what's happening to the second derivative of position with respect to time, and then we're just going another level and saying what's happening to the third derivative of position with respect to time. Now, I don't know. I mean, I know some of them. You know some of them. The last one sounds intimidating. We've never talked about it before. How could we possibly know? Well, in order to get that last one, maybe we want to look at patterns. Maybe so this is the question, right? The question is what's happening to the magnitude of velocity, what's happening to the magnitude of acceleration, what's happening to the magnitude of jerk. Well, a suggestion for how to answer it, suggestion, pro tip, is if you don't know the last one, but you think you might be able to answer the first two, which I think you all can, in order to answer the last one, maybe looking at pattern recognition would help. And the truth is, there is one more that I actually know, even though the question hasn't been asking it. Like I could back up, like hint, back up to see a pattern. I could back up to position. In other words, before I even get to dx dt, before I get to the derivative of the function, why don't I look at the function itself? Right? So let's just look at x. Now, this is not a trick question. I'm trying to break everything down into simple questions that I can answer. I'm not trying to trick myself. So I'm looking at the position first. I'm not looking at negative signs or positive signs, just the magnitude of the position. So originally, the mass is at a position 0.15, and it moves into position 0. right? So it's going from 0.15 to 0. I'm going to ask you all, you can just shout out or put in the chat just to make sure and you can get points. And I'm not trying to trick you. I'm just trying to keep us all together. So if the position changes from 0.15 to 0, is the position increasing, decreasing, or staying the same? I'll say anybody, you could shout out, you could put in the chat. It's not a competition. Awesome. You could put in the private chat, right? Either one, fine, because I'm not going to say awesome, awesome. I see like 3 answers in the public chat. Thank you. And I see 1 in the private chat. Thank you. Oh, I see more in the private.
What you just said.
Yes, I can. The question is, and by the way, you can all, even though there's tons of answers in the public chat and you can see each other's answers, I'm not saying whether they're right or wrong. So don't, I'm asking, because I'm going to do this for each one of these. I'm asking if the position of the mass changes from the beginning, from 0.15 to 0, would you call those numbers decreasing, increasing, or staying the same? The magnitude is going from 0.15 to 0. So that's the question. Okay. So I've seen the direct chat. Okay. So I see a bunch. Thank you. Every single one of you that answered, please. What portal? The portal for right or for wrong. Because you just had the guts to, you get the point. Like, but really, so many people said decreasing. In fact, many people in the chat said decreasing. I totally agree with you. I totally agree. That's awesome. Now, if you happen to have gotten it wrong, you could even submit for points for me. So, okay. So the position's decreasing. I'm going to go on. What about the derivative of the position, the velocity, the magnitude of the derivative? We're talking magnitudes here, like, right? So to make it simpler, not harder. So if we're going to the velocity now, the speed now, the speed started at 0, and then it came in to a number of 3.87 meters per second. So again, shout out or chat, private or public. The speed, did the speed decrease or increase? If it went from 0 to 3.87, awesome. I see something in the private chat, and it's private, so I'm saying it's awesome and correct. That's one person. 2 people in the private chat, awesome. See, private chat's such a 3 people in the private chat, awesome, and 1 person in the public chat, awesome. That's good enough for me. Awesome, awesome. That's it. Okay. So I've got like 5 answers. That's good enough for government work. And all of you are saying increase. I totally agree. I am not trying to trick you. Am I trying to trick you into thinking physics is easy? No, I'm trying to show you that physics is easier than you think when you break it down into tiny questions. That's our job. The hardest part of physics is breaking it down into tiny questions. Anyway, and this is ultimately to make a point. It's not anyway. So the position is going down in the first quadrant. The position is going down. The speed is going up. Now the acceleration is going magnitude. The acceleration is going from this enormous number of 100 meters per second squared at the like you found it in question 2 of the homework, right? I mean, technically the acceleration was negative 100 meters per second squared, but that negative sign just meant pulling in. It meant the force is pulling it toward equilibrium. The negative is direction. I'm not worrying about that right now. So the force was huge at 0.15 meters. And so the acceleration magnitude was huge. It was like 100 meters per second squared. The potential energy was huge. So but then it comes all the way in and it's 0 at equilibrium. So what happened to the acceleration? Did it go up or did it go down? I'm asking, the acceleration, all y'all, and again, also for the right or wrong thing, if those of you who don't know, if you answered twice today, can you put up like 2 screenshots and say yes? And get to, and can you do this again tomorrow? Yes. And get more points? Yes. Not tomorrow, but next. So the acceleration, is the acceleration decreasing or increasing? Awesome. I see 2 answers. 1 is private. 1 is 4 answers. Great. That's good enough for you. Okay. Awesome. But if anybody else wants to say increasing or decreasing on the acceleration, don't be. So yes, I agree with the private chat people and the public chat people. It is, I don't know why the color tone changed, but it's decreasing now. Now we get to jerk. This guy, we get to jerk. That's what we've never thought about before. Like, how would you know? I mean, the derivative of acceleration with respect to time. How could we know? what that's doing. In fact, a lot of people in their homework tend to put constant because it always, and that shows you're a physics student. If you put the answer to this last one as not changing, you're a good person. You've been paying attention because that was generally the case in a lot of physics 203. Like with gravity, that's true. Gravity causes an acceleration, it causes a change in velocity, but it doesn't cause a change in the change. That's why we love gravity. Gravity, the acceleration in free fall is 9.8 all the way. So the change in that is zero. So if you put no change for this question on this homework, it means you've been paying attention to something, but it isn't the case here. Here, first of all, if you just look at this pattern, if you look at this pattern, it's reasonable to guess. It's reasonable to conjecture that the change in acceleration is actually going up. And it is. It is. And we can show that really quickly. I don't know why I'm in red now. Sorry. Okay. This is going to set us up now for question 9. Can we verify like what's going on with the derivative of acceleration? Well, maybe I'm skipping a few steps here, but we've said now a million times, question 1, 2, and 3, we've said F net equals ma, and the only force acting on the spring is negative kx. So negative kx equals ma. Oh, but we're also saying, sorry, this is like a step 3 thing. Sorry, I'm sort of skipping. We also know by definition, acceleration, instantaneous acceleration, always in math and physics, the definition of instantaneous acceleration is second derivative of position with respect to time. So to say that negative kx equals ma is to say negative kx equals m d2x dt squared, like m times the second derivative of, of position with respect to time. So the second derivative is directly proportional to the function. That's what Hooke's law means. You might want to put this in your notes. The second derivative is directly proportional to the function x. If x goes up, the second derivative goes up. If x goes down, the second derivative goes down. If x gets doubled, the second derivative. In other words, that's why the arrows for x and d2x were in the same direction, because they're directly proportional to each other. I mean, let me put it another way, because we're going to use this for question 9. In other words, d2x dt squared equals the second derivative in time equals a constant times the original function. By in this case, the constant is this. Or strictly speaking, it's -1 times a constant, but -1 is a constant also. So So whatever happens to x has to happen to a, but I can take the derivative of both sides. And I can say, right, if I can take a derivative of one side as long as I take the derivative of the other side. So that shows, if I take the derivative of both sides, that the jerk is directly proportional to the derivative of position, i.e., of velocity, right? Well, that means the pattern has to continue. It means that when I just conjectured that this pattern was going to go on forever, it's actually true. Whatever happens in Vegas stays, whatever happens to the velocity here, here must happen to the derivative of acceleration here because they're directly proportional to each other. And could I go the next step? Yes, this must be. Oh, sorry. Oh. So IE, and tell me if I'm getting all confused in the pages. I mean, if I'm confusing you and you want me to go back, just tell me. What we're saying, so I'll read my handwriting. So what I'm saying is the pattern of derivative alternation must go on forever, according to this little quick argument we just made. So, in other words, if you already were picturing, once you were picturing that oscillation means going back and forth forever, and then once you realize, well, so once you realize that oscillation means, at least ideal oscillation, oscillation governed by Hooke's law, means going back and forth forever, the positions going down and then up and then down and then up. What I'm saying is, yeah, and it's not just the positions in space that are going back and forth in a pattern forever. It's every single derivative of those positions. The speed, so when the position is coming in towards zero, the speeds are going up. But then when the positions are going out towards negative 0.15, the speeds are going down. And then the speeds are going up and then the speeds are going down. So just like position is going down and then up and then down and then up, the speeds are doing the same thing, but reversed. The speeds are going up and then down and then up and then down and then up forever. But then so are the accelerations, but flipped. The accelerations are going down and then up, just like the positions are, and then down and then up. And this doesn't stop. We're used to constant acceleration. We're used to somewhere the buck stopping and some kind of derivative eventually flattening out or equaling zero. There's no derivative doing that here. The change in the change in the change in the change is changing up and then down. So oscillation, it's very simple, but it's very deep. going back and forth means every aspect of your motion is going back and forth and back and forth. That's what we're saying here. So that's interesting. It means there's like a lot of stuff worth looking at here. So then when we get to question 9, step 2, the question for question 9 is a really simple classic physics question. You name the time. I mean, if I name the time, can you name the place? At t equals 1, predict where the thing is. There couldn't be more seemingly straightforward about that. but but answering it, so well, okay, and first of all, there's nothing special about t equals 1 second. That's just a numerical example. What we're really asking, like what we want, is some kind of formula, some kind of equation. If you name the t, if you plug in the t, can I spit out the x? So we're looking for something like x equals 1/2 at squared plus v naught t. Only that particular function won't work. Hold on. All right, let me back up for a second. Our goal here, before I even get into step 3 or anything like that, just clarifying in step 2. That doesn't really help, does it? I just want to clarify that this question sounds like it's asking when t equals 1, what is x? I'm now translating and saying, what we're really looking for is when t is anything, what is x? How does x depend on t? That's what we're looking for. What is the function? Well, okay. You might think it's like x equals 1/2 at squared. What x equals 1/2 at squared um says is, like we often say in physics, well, if you want to predict the position, we need to know the acceleration. But here, the situation is telling us what we just found out a minute ago is if we want to know the acceleration, we need to know the position. Step 3, in other words, we have F equals ma, we have F equals negative kx, and we have that a in general is d2x dt squared. So what we have is negative kx equals ma. That's our step 3. I mean, well, really, well, actually, sorry. So step 4, I guess. Step 4, in this case, we have that negative kx equals ma. In other words, negative kx equals m dx. Right? We have that. And to simplify, to rearrange it, we have this. Now, what this is saying is you want the x for some function of t. Normally in physics, or typically in physics, in order to predict where something is at some moment, we would need to know the rate at which it's accelerating. And we would plug in the rate at which it's accelerating and infer, maybe infer something about the velocity and then infer where it's going to be in a certain amount of time. Here we're saying, well, yes, you can use the acceleration to get the position, but the acceleration is changing at every position. If you want to know the acceleration, you need to know the position. And position's the thing we're trying to figure out. There seems to be a circular reasoning here. I'm just going to rewrite again. We have, in other words, we have in here all of the information that we are looking for. We have x being treated as a dependent variable. We have t being treated as an independent variable. That's what we want. But we want it in some simple, straightforward package. We literally want an expression where x equals blah, 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 times t. We want an input-output direct statement. This does not give us that. This gives us, if you input x, multiply by a constant by a negative sign, you'll get back some kind of derivative of x. How can we solve this? Do we have to have taken a class in how to solve the? No, don't. Because if that class is taught by people who learn things that were figured out by people who never took a class, who just came across this in physics and had to figure it out. How how can we? So what we're trying to do with 14 minutes, we're trying to look at an equation that expresses a derivative or a second derivative as a function of a dependent variable. Oh, great. Oh my God. All right. There's a comment in the chat, a private comment. I'm not going to say who it is, but a really smart comment that is going to help me move this along. Okay. I'm going to read that comment in a second. Great question. I'm going to use it in a second. But I'll just repeat what we are trying to change. We're trying to get back from like a derivative or a second derivative back to an original function. That's what we have to do here. Now, anybody if you're thinking in the room, well, we've got some kind of derivative, but we've got to get back to the function. Doesn't that call to mind integration? And that's what the private chat thing says. Can't we do integration so we can get back to time? That's exactly the right thing to think. That means you've been doing calculus and physics. If you're thinking the way to do derivatives backwards at some level is integration, you are correct. The thing is, it's going to be a little bit hard here. We can't do it directly here. We have to do a little bit more work than that, or we have to think out of the box a little bit because I think I just wrote it on the first page. The quick answer is what makes this. This is an equation that has a derivative in it, but it's more than that. It's what we call a differential equation. And again, I'm assuming you did not ever take a class in these things. You don't need to have, neither did the first. You need to look at it the way a physicist would. Basically what I'm saying is if we had d2x dt squared equals negative k over m times t, if it said that the derivative was some kind of function of what it should be, of the input, then we could maybe integrate directly and integrate directly again. We could integrate in terms of dt and get what we wanted. And ultimately what we're going to do is something like that. But what the problem here, the thing that makes this interesting is this circular reasoning, this feedback loop, that it says that the acceleration per time at any given moment isn't based on time. It's based on place. It's saying the rate at which the position, it's saying that some kind of rate of change in position with respect to time is based not on time, but on position. If you get confused every time I say that, join the club. We're saying that the change in output is not based on the input, but based on the output. That's what makes this a differential equation, and that's what means we can't just simply integrate, even though ultimately that is what we're doing. Like the person who's written into the chat totally knows what's going on. Um, but we're going to have to do something more exotic than that. Whether we are mathematicians of the first time looking at this or the most advanced type, or we are scientists, physicists, either way, what we're going to have to do here is what we did in question 8. And this is what people do. This is puzzle solving. We are going to have to conjecture. We're going to have to come up with a good guess based on our experience and then verify the guess. Conjecture and verify, i.e. guess and check. The guess might not sound very scientific or mathematical to you. It may sound more like art to you, but the truth is science and math ultimately really are art. The guess might not sound very scientific to you, but only someone who is really versed in science and math would even be able to make the guess. And the thing that really makes it math and science is then once we make a guess, we're going to be able to check if it's right or wrong. We just need something to work with. We'll be able to check, analytically whether it's right or wrong. Now, how can we make such a guess? We use the fact that we're physicists, that we can picture the system, that we've been in the lab and we also use our math experience, but we use the fact that we're in the lab and we have seen springs go back and forth. If we're trying to guess a function x as a function of t, right? We're trying to guess what does x do as a function of t? We need an expression. Well, we know x is going back and forth forever. And in fact, has a derivative that's going back and forth forever, which has a derivative that's going back and forth forever. Or on axes, it's going up and down, right? Furthermore, we know that the mass starts, it doesn't start at zero. If it started at zero, it wouldn't go anywhere. It starts somewhere other than zero called x naught, right? And we know it comes into zero and then it goes past zero and goes down to something, to negative x naught. And then we know it comes back and it goes back and forth forever symmetrically and smoothly. It doesn't go into jagged, like it doesn't go like a cartoon. So we guess the most simple. We always start with the simplest, and then until it doesn't work, and then we try something slightly less simple. So just from our lab experience alone and our math experience, a kind of function to describe what this x is doing is like a cosine function. Cosines go back and forth smoothly forever. They start away from the origin, and they have derivatives that go back and forth forever, but in the opposite direction from them, right? Doesn't it seem like it has the properties we're looking for? In fact, very specifically, what we're looking for is an x, which we're looking for an x, which when you take two derivatives of it, you get back some version of it times a negative sign. Isn't that true of cosine? You take a derivative of cosine, you get negative sign. You take a derivative of negative sign, you get negative cosine. Doesn't that look? I'm not saying it's right, and I know we only have 7 minutes, but I'm saying whether this was the first time anybody ever saw a differential equation or the way they do it now, what we do is we use our experience. We're looking for a function that when you differentiate it twice, you get back that function times a constant times -1. From the lab experience and math experience, a good thing to guess is a cosine function. So I'm going to guess. We're not done. Sorry. And we have 6 minutes. Okay. I'm going to conjecture. I'm going to conjecture some kind of cosine. What do I mean by some type? I'm guessing that x depends on t in a cosinusoidal way. Some kind of cosine. That's a guess. But let me be more specific. And now I'm going to test the guess, and you'll see I'll be able to test it because the equation says what has to happen. If you take two derivatives of this thing, you have to get negative times k over m times the thing itself. That's what the equation says. So and I can take derivatives. Derivatives aren't as hard as integrations. So I'm sort of guessing the integral, like based on what the person said in chat. I'm sort of guessing what the integral is, but then I'll check if I'm right by differentiating. Since for everybody, differentiating is more straightforward. The only thing is, I'm a scientist. I'm a physicist. I know there's going to be more information here. It's not just going to be x equals cosine t. That's too simple. How do I know? Well, first of all, you can't, because t is measured in seconds in the lab. And when you take the cosine of first of all, you can't take the cosine of a second. And second of all, what you're supposed to be getting as your final answer is meters. And certainly cosine does not spit out meters. I know my final answer has to be in meters and my input has to be in seconds. So there's got to be something in here whose units will cancel out the seconds and put in radians, because I can only take or degrees, but we're in like sophisticated land now. So I can only take the cosine of something in radians. There has to be a constant there measured in radians per second. I'm going to call it, you can call it whatever you want. I know in AI and all in ChatGPT, they call it B or A or something. We'll talk about that, or K, but you can call it whatever you want. I'm going to call it omega. Similarly here, so then cosine, I'm going to take the cosine of some type of constant times t, and then cosine will spit out a number anywhere between 1 and -1, just a raw number. So first of all, I've got to multiply by something that's measured in meters in order for my answer to be in meters. And in fact, if I think about it, I can this is easier. I can call this x naught, or what they call on the web A, because basically this x has to, when t is 0, when t is 0, cosine of 0 is 1, it's the maximum will ever be. Well, that's the maximum place where I put the mass in the first place, like what we called x naught in the problem. I'm saying that a little bit quickly, but if you think it through, you'll realize. So my guess with 3 minutes left, based on units. Now, I don't know what omega means. I just know there has to be something there. There has to be a constant before the t to make the units work out, and there has to be a constant before the whole thing to make the whole thing work out. So I'm guessing that x equals x naught cosine omega t. That's a guess. But now to verify, I take a derivative. Now remember, I'm going to verify. What's the condition? It must be true that the second derivative of x with respect to t must equal this constant times -1 times x itself. If I take two derivatives with 2 minutes left, and if I go when it's 10:40, you can leave. If I go like a minute over, just stay first if you can stay. But this will be in the notes anyway. The point is, when I take two derivatives, I've got to get back itself. I've got to get back x, but times a constant times -1. Well, I'll do it fast. If I take one derivative of the above, you show this, and you may have to practice, but from chain rule and from trigonometric derivatives, I get negative x naught omega sine omega t, right? Because derivative of cosine is negative sine and the chain rule. If I take another derivative, if I do that again, I'll get negative x naught omega squared cosine omega t. In other words, negative omega squared x naught cosine omega t. We've got 1 minute left. I'm going to write that on the next. If I take two derivatives, I get negative omega squared x naught cosine omega t. But this whole thing right here, x naught times cosine omega t, that is x, right? That's what I guessed. So according to this guess, that is x right there. So if I guess this, if I say that x equals x naught cosine omega t, then indeed I get d2x equals negative omega squared x. Like it means I have guessed something where very good. I see that in the chat. Very good. Yes. I'm just going to keep going for a second, but yeah, it means I do get x back times some constant times a negative sign. That's exactly what I wanted, i.e., this guess works as long as by omega, that omega thing that I didn't know what it was before, if omega squared means the same thing as k over m, then indeed d2x dt squared equals negative k over m x. So that is with 1 minute, it's 10:40, but so that is from now on, this is what you get from the web, but it's true. I've just verified and figured out, or in other words, x from now on must equal negative, it must equal cosine of omega t, where omega is the square root of k over m. So this is the answer. So if you just plug in the values from in radians, if your calculator is in radian mode, and you plug in 200 over 0.3 times 1, you will get the correct answer of 0.116 meters. We're going to talk about that more slowly and carefully on next class, I promise. But that's bottom line. You have all the knowledge you need. You make a guess based on lab, and you verify that guess based on taking two derivatives. And even if you didn't call the thing omega, that doesn't matter. You can call whatever you want. But that constant there that had to be there from units must equal square root of k over m if this thing worked. So I'll leave it at that for a moment. If you want to hang out and ask any questions, you can, but good job. But that's the end of the homework 1A. Homework 2 is blah, blah, blah. You've been in great class as usual. I'm going to pause the recording, but yes, have a great weekend. Have a great and a good day. Yes, I'm pausing, but I'm not going anywhere. Recording or stop.